Hi everybody, this is Mr. Williams joining you today. We're going to be looking at a combustion problem as it would have been appeared on an AP exam back in 2005. This combustion problem not only has combustion, but it also has a little bit of colligative properties as well as some organic chemistry at the end. So we're going to look at all three, and this really encompasses a lot of different topics, but the main part that I'm worried about today is the combustion, which happens to be part A of our problem. Now, all of these questions will be concerned over a compound containing carbon, hydrogen, oxygen, but we'll divide it into three different parts. Let's look at the combustion part first. First off, remember, if we're going to have a compound that has carbon, and we don't know, it's X, and hydrogen, which we don't know, and we'll say there's Y hydrogens, and it has oxygen as well, we'll call that Z, it's really hard to determine what that mass would be unless we have some combustion data. And let's think, any good combustion problem, if we're going to combust in our reaction, we have to react with oxygen gas. When it combusts, you're going to get carbon dioxide, because we will always assume complete combustion, and water, both of which are gases, because if we're burning it, water will vaporize and carbon dioxide is a gas. The key to this problem is trying to determine how do we get the amounts for each individual element. And that comes looking at our balanced equation. If we just look for carbon itself, carbon is found in our compound, and it is only found in carbon dioxide. So if we think of this in terms of a percent composition idea, we can determine the amount of carbon that we have for both our original compound by using the carbon dioxide amount. For example, if we know that we had 1.9061 grams of carbon dioxide, all of that carbon would have had to have come from the original hydrocarbon compound. Well, the molar mass of carbon dioxide happens to be 44.01 grams per mole. We know that for every carbon dioxide, there is only one carbon atom contained in that molecule, and the molar mass of carbon is 12.01 for 1 mole of carbon. If we look at those together, we would find out that by analyzing the carbon dioxide, we would get 0.5202 grams of carbon for our compound. And that had to have been the same amount of carbon that was in the original compound, because they are the only place you can find carbon in our balanced equation. Hydrogen is a very similar idea. Hydrogen is found in our original compound, but the only place hydrogen is found on our product side is in the water. So if we look at the percent composition of hydrogen in water, we can also get the grams of water. And so that's a very similar calculation to what we just did. And we're going to now start with 0.3370 grams of water. And we know that 1 mole of water happens to be 18.01 grams. But the difference here, water has 2 hydrogens for every 1 mole of water. That's different from where we were with our carbon dioxide, where it was a 1-to-1 ratio. Now we got a 2-to-1 ratio. And finally, the molar mass of hydrogen is 1.008 grams of hydrogen for every 1 mole of hydrogen. And that'll give us a value of 0.03771 grams of hydrogen. Now, what does that do for our final amount? This compound, if you recall, not only has carbon and hydrogen, it also has oxygen. That's what makes this problem a little more difficult, because oxygen is not just found in our original compound. It is also found from the air. We needed the oxygen for this substance to combust. Unlike carbon, where there was only one product it was in, oxygen is found in two products. So again, that makes it difficult as well. The great thing is that we know the mass of the original sample. And the mass of the original sample happens to be 0.7549 grams of that CXHYOZ compound. If we subtract, because of our law of conservation of mass, the amount of carbon, 0.5202 grams of carbon, and the mass of the hydrogen, 0.03771 grams of hydrogen, that we found through our combustion analysis, that will leave us with our amount of oxygen. And the amount of oxygen, when we do the subtraction, is 0.1970 grams of oxygen. That's how you calculate the individual masses of them. The second part of this problem is, once we know the individual masses, it'd like us to know what is the empirical formula of this compound. So we need to figure out how many moles of each, because remember, we cannot compare grams. The mass of one element compared to the mass of another element is not comparable. Only the moles of one element compared to the moles of the other element will be comparable. And so let's first look at our elements. We have carbon, which was 0.5202 grams of carbon from our original problem. The molar mass of carbon happens to be 12.01 grams, and that gives us 0.04331 moles of carbon. If we analyze hydrogen, we found that there were 0.03771 grams of hydrogen to start, and we know that our molar mass of hydrogen happens to be 1.008 grams, for a total of 0.30371 moles of hydrogen. And then finally, we learned what our oxygen amount was, and our oxygen, we said there was 0.1970 grams of oxygen in our problem. 1 mole of oxygen is 16 grams for its molar mass, and that happens to be 0.1231 moles of oxygen when we go to solve this. We had grams, we've changed it to moles. Now what we do is we divide by the smallest number of moles in our problem, which in this case happens to be our moles of oxygen. So we're going to divide each of these answers by 0.01231 moles, 0.01231 moles, 0.01231 moles. And by doing that, we're going to hopefully find our empirical formula. Now, that gives us answers of, for carbon, 3.518 moles. For hydrogen, that's 3.039 moles. And for oxygen, it's exactly 1 mole. Unlike some problems where you think you can just round, the fact is that we now have an amount of moles of each one, where the carbon is 3.5 moles of carbon to 3 moles of hydrogen to 1 mole of oxygen. Because of this half right there, instead of rounding, we have to double it all to find our empirical formula. And that actually means we would have 7 moles of carbon to 6 moles of hydrogen to 2 moles of oxygen. And the empirical formula is going to be C7H6O2 for your final answer. That's the part A of this problem. This part is then used as we move forward. The second part of this question is now looking at freezing point depression. And it says a 0.5246 gram sample of the compound that we just found was dissolved in 10.0012 grams of lauric acid. And it was determined that the freezing point of the lauric acid was lowered by 1.68 degrees Celsius. The value of the freezing point depression constant of lauric acid is 3.90 degrees Celsius per mole. If we assume that the compound does not dissociate in lauric acid, letter I, calculate the molality of the compound dissolved in the lauric acid. Well, remember that our equation for freezing point depression, change in temperature freezing, is equal to the freezing point depression constant for the solvent that we are using times the molality of the solution times the Van Hoff factor of I. Sometimes it's referred to as the dissociation factor. Since this problem says that it does not dissociate, this causes I to equal 1 for this problem. What do we know? To solve for molality, if we rearrange our equation, change in temperature, freezing, divided by our freezing point depression constant, will give us that molality. And it tells us in our problem that we lowered the temperature, or our change was 1.68, so 1.68 degrees Celsius, and that the freezing point depression constant is 3.90 degrees Celsius per mole. When we solve that problem, we get a final answer of 0.431 mole. Now, they want us to calculate the molar mass of the compound from that information. And if we know molality, if you remember, molality is equal to moles of solute divided by kilograms of solvent. They told us the amount of lauric acid that we had, and we now know the molality, so we should be able to figure out moles, and they also tell us the grams of that sample. And remember, molar mass of any compound has the units of grams per mole. So if we know grams and we know moles, we can figure out molar mass. So let's figure out how many moles of the solute we actually used. To do that, our molality was determined to be 0.431 mole. And that must mean we are going to have 0.431 moles if we had 1 kilogram of lauric acid. We don't have 1 kilogram of lauric acid though. In this case, we have 10.0012 grams of lauric acid. So if we change that into kilograms, there are 1 kilogram is 1,000 grams of lauric acid. That would give us an answer equal to 0.010012 kilograms. We have kilograms. Now we also have our molality. So to solve this out, we have 0.431 mole times our mass of 0.010012 kilograms. That'll equal 0.00431 moles. of our solute. Since there happens to be 0.5246 grams of our solute divided by 0.00431 moles, our final molar mass equals 122 grams per mole for our final answer. So it took a little bit to get there, but all we did is we first found moles using our molality equation and the answer from part I, and then divided that by with the grams that we had given in our problem. Part C says, without doing any calculations, explain how to determine the molecular formula of the compound on the answers to parts A2 and B2. Well, remember, empirical formulas are the simplest formulas of a compound, but they don't necessarily mean the true formula. The molecular formula is the true formula of a compound. And just to make sure you can see what we mean, if we really wanted to find a multiple, because molecular formulas are always whole number multiples, including one of the empirical formula, you may think of taking the molar mass of the molecular formula and dividing it by the molar mass of the empirical formula to equal that whole number multiple for our final formula. Okay, now the key is you have to describe this without using a calculation. So the way you may want to think about doing this is that the molar mass should be divided by the empirical formula found in part AII, which, if you remember, was C7H6O2. So if we take the molar mass that we found in the last problem and divide it by the empirical formula's molar mass from part AII, that will give you a whole number multiple. That can be used to write the molecular formula. By multiplying each subscript by the multiple. You would want to avoid using the idea of showing this here. You don't want to show that actual formula with the way this question is written, but knowing this in the back of your head, it helps you to write out an explanation. The last part of this problem, part D, says that further tests indicate that a 0.1 molar aqueous solution of the compound has a pH of 2.6. Identify the organic functional groups that accounts for this pH. Organic, organic, organic. Remember, organic compounds are mainly carbon, hydrogen, and oxygen, and there is some nitrogen in there as well. If the pH is 2.6, if we think of what our pH scale is, 0 to 7 to 14, anything less than 7 is an acid, anything greater than 7 is a base, and of course 7 is neutral when we think of this problem. Well, pH is 2.6. That automatically makes this substance an acid. Now we have to think, what is the acid functional group in organic chemistry? The acid functional group that should immediately come to mind, hopefully, is a carboxylic acid. And carboxylic acid groups are infamous with that COOH group, COOH ending. If we were to draw them out, it would have that carbonyl carbon connected with a double bond to oxygen with an OH. The rest of this molecule could be any carbon chain, but it would have to have an ending of COOH. If you identify this functional group in paragraph form, such as just basically saying that it has to be an organic acid or a carboxylic acid, you would have earned a point for this. On an aside, what would have happened if they said the pH, instead of being 2.6, happened to be 10.7? That would have made this a base. And if it was organic chemistry, the base most likely would have been an amine group. But if you think about it, this could not be an answer to this question, or this exact question could not have been asked, because going back to our original equation, it told us that the compound only had carbon, hydrogen, and oxygen. For an amine group, you obviously would have to have some nitrogen involved, and that isn't in this question. But it's something to keep in the back of your head as you're taking the AP exam here in a couple of weeks. I hope this helps on combustion problems, and if you have any more questions about it, you can always talk to me in class. Have a good one.